All right, hello again, chemistry students. If you're at this point, you're ready to see some notes about how to calculate energy problems. Specifically, this is Unit 3 in the last section that you're in before the test. And I want to point out that this is actually an optional video to watch, an optional section to do practice from, because we're in Learning Goal 3.7, as you can see right here, and specifically this section is all about Level 4 material to score a 4, which again, remember, our hope is everybody's here, so Level 4 material is above and beyond and optional. Specifically, we're going to work on solving problems involving energy transfer and changes in state, not just being able to model them with our charts and diagrams, not just be able to make predictions about what's going on with particle models, but actually calculating with numbers. So we're going to be using equations, calculating a number in joules for things that are changing state or changing temperature right now. So again, if you're interested in being able to do Level 4 questions on a quiz or test, then you should definitely watch this, do the practice. If this is outside your goal of this class, then you can just move right ahead and not worry about this information. So to help do this, I'm actually going to go back to our Icy Hot Lab and the graph that looked like this, and this is a really good way to show you examples of how to calculate. So one thing that you did is you broke this graph into 3 sections. Section A right here, where there was a low temperature plateau at 0. Then right here is section B, where there was an increase in temperature, a slope line. And then you had a final plateau at the end, which you labeled region C, where it leveled off. And so I'm gonna use those 3 regions because each region, there's something different happening with that system that started out as ice, and there's 3 different ways to calculate that. So I'm gonna switch over to some notes. This note document will also be available on Canvas as well. So if you want to skip the verbal instruction that you're getting right now and you think you can understand these just by looking at them, then you can exit out of here and open up the same document will be on there as well. So we're going to start with region A. Region A is where we had that low temperature plateau and it was at 0 degrees. So I'm just going to click back there for a second. Notice temperature remained constant during this region right here. No change in temperature was occurring. The thing that was occurring, if you recall, was that the ice, because of the heat being transferred from the hot plate, was melting. It was going from a solid to a liquid. So that's what we're going to calculate then for region A. In addition, this is what your diagram should have looked like. You already did that. You checked those answers. So we started out with low temp, a low interaction because it's a solid, and in the end, again, for section A, no temperature change occurred. So notice that the ETH here, same height as here, but the EI went up because that solid went to a liquid. There was energy going into the system for this to happen through Q heating, and the direct source of that was the hot plate. So what we're going to do now is calculate, well, how much energy did the hot plate have to put into that system for this change to happen? And so since what was going on in region A was solid to a liquid, I'm going to talk about the mathematical model that you use to calculate that. This would be the same equation if you were going from liquid to solid. So that's why I have a double arrow here. For us, though, it's solid to liquid because energy got added to the system. And so here's the relationship. To find Q, that number, is equal to mass times a value called HF. And I'm going to talk about what those all mean. Q, as you know, is our energy transfer due to heating. Energy units are always a J, which represents joules. Our energy unit are joules. So we're going to calculate how many joules, again, got transferred from the hot plate. M is what it always is, mass in grams. So the amount of ice that was there is directly related to how much energy it's going to take. More ice, more energy to melt it. Kind of makes sense because there's more particles there that we need to change. And then H of F is a special variable called heat of fusion. Heat of fusion. And the units for that are joules per gram. This is a value that is unique to every substance, and it tells us how many joules for every gram present it takes to change it either from a solid to a liquid or liquid to solid. Again, it's unique for every substance, and it's a reference number that you can look up. For water, that happens to be 334, so I have that number right here. Again, that's for water. So what that means is for every gram of ice, it takes 334 joules to melt it. So if we know how many grams we have, and I'm just going to assume, let's say we had 100 grams. If we had 100 grams of ice, we need to multiply that by this heat of fusion factor, and that means our total energy needed from the hot plate to melt all of 100 grams of ice would be 33,400 joules. So again, a solid liquid, liquid solid phase change, mass times heat of fusion. And again, your units then are joules. Okay, we're going to switch over to region B now. So I'm going to scroll down. And I want to remind you that in region B, we kind of starts from here and it goes up to here. And so notice the thing that's happening with the graph on region B is there's a temperature change from that 0 to approximately 100 degrees. During this time, you should have observed in the video that nothing was changing with the water. It remained a liquid the whole time throughout, but as indicated by the data, the temperature was changing. It was going up. So because of that, this is what the bar chart looks like for that. Started out 0 degrees, so low thermal. In the end, it ended up at a high thermal because it went up to 100. It ended as a liquid at the end of region A because it melted, so it started out as a liquid, and again, the whole time up until 100 degrees, it was still a liquid. The thing that was changing was the temperature, so notice that's why ETH changes. Again, this is still due to an input of energy into the system by the hot plate, and again, that's through heating, so we're going to calculate Q. So the thing that was happening in this region was a change in temperature. So here's the relationship that you always use for a substance that is changing temperature. It is different than changing phase of solid, liquid, liquid, solid. This time Q depends upon M again. It depends upon what we call delta T and C. So let's talk about what those mean. Q again is energy. So same as before, how much heating the hot plate was giving, and our unit for that is joules again. So that's what we're going to calculate. M, of course, is mass. Depends upon, the energy depends upon how much stuff is there, so that's a factor in grams. And this triangle T means delta T. Delta always means change, and so the large T in this is temperature. So the amount of temperature change also determines how much energy is going to be needed, which again makes sense. If we're talking just about a little bit of temperature change, we don't need as much energy transferred if we're talking about a huge temperature change. Whenever you find change, you always take final minus initial. So that's what TF minus TI means. And again, since we're talking temp, we're going to be in degrees Celsius per unit. So the change in temp is important. The last one, C, is another very unique value for all substances. This time it's called specific heat. Specific heat. Every substance has a different specific heat. And the units you'll see are joules per gram degrees Celsius. And what this value is, it tells you how much energy it takes to change 1 gram of a substance 1 degree Celsius. Again, one gram of a substance 1 degree Celsius, how much energy. That value for water, it shows up here in this work I'm going to talk about, 4.184. That is the value for water. If we were talking about a different substance, we would have a different value there. It's very specific for that substance, hence the name specific heat. So for water, that means that for every gram, for every 1 degree and 1 degree Celsius temperature change, it takes 4.18 joules of energy. So we're not talking about 1 gram. Remember, we're going to use 100 grams. And we're not talking about a 1 degree temperature change. We're talking about a 100 degree temperature change. So we have to multiply all of these to get our total. So our mass is the same system, so still 100. The graph tells us that this was the temperature change that occurred between 0 and 100, which makes sense because water melts at 0, boils at 100, so that was the difference that occurred to get to that point. And again, this value for water, 4.184. And when you multiply those, our number is 41,800 joules. That is the amount of energy needed by the hot plate to go into our system for region B to change the temperature. Okay, next we're going to go then the last region, and let me remind you what that looked like on the graph. We have another plateau here at approximately 100 degrees, and that is the key value for pure water. Will at 100 degrees do what you saw happening here on the video, and this is where it was boiling. It was going from a liquid to a gas. So notice when that happens, there's no temperature change that occurs, but we do know that that's the critical value for water to change state, and we saw that happen in the video. So here's what our bar chart looked like. That region started out at 100 degrees. It ended at 100 degrees. So there was no change in thermal. However, there was a change in interaction because it started out as a liquid, but as we know, if we let that continue to go, all of that would be changed to a gas. So we have a high bar then because we had a change of state. Still have energy going into the system from the hot plate. And so that's what we're going to calculate is how many joules of Q transfer by heating happened. So now we're talking about a phase change, much like region A, but this time we're talking about liquid to a gas. Or if you're doing gas to a liquid, it would be the same numbers and same relationship that you would use. So this time, our Q is directly related to M again, which is mass, and then another value called HV. This time, it's called heat of vaporization. So here's what these variables represent. Q is the same, energy in joules. M is the same, mass in grams. HV, heat of vaporization. And the units for this, much like HF, are joules per gram. This number tells us how much energy it takes per gram of a substance to either change it from a liquid to a gas or gas to a liquid. It's a different number than it was for heat of fusion, so that's why we have a different variable, different number. The number for water, which is our substance in this case, is 2,260. So if we had 1 gram of water changing to a gas, it would take 2,260 joules to cause that to happen. Again, we don't have 1 gram. We're assuming we have 100 grams. So we have to multiply those two to get our total. It would take 226,000 joules. Again, energy supplied by the hot plate into that system to cause all of that liquid to change to a gas. So if our question then was, what's the total energy from the hot plate from here to here, all we would have to do is add up those 3 numbers that we just calculated from those 3 regions to get our total. This number plus this number plus this number. So these are examples of all the different things that might happen. Sometimes you might have problems where maybe you know the energy and you have to work backwards and find the mass, perhaps, or find the change in temperature that occurred if it was a change in temperature problem. If you have a situation where you have multiple things happening, change of phase and change of temperature, remember you have 2 things that you're going to have to add together so that you get the total energy that's going on in those problems. So there's some really good practice. I have paper copies, or you can go back to Canvas and you can download those or view them and do problems and check your answers. And then if you're interested again in this level 4, there's a quiz with questions for that. And it will be helpful for the test. So get out your calculators and calculate it up this time.